Hey guys, welcome to my video. In this video, I'm demonstrating you my project named Multi-Echelon Inventory Management. Multi-Echelon Inventory Management gives us the optimal inventory quantity and order cycle for a given set of graph of inventories. So for a typical inventory management, we don't have to estimate the order cycle for a given inventory. Instead, we can compute the optimum order cycle for the given network of inventories. Now, this is the grid world object which defines the network of inventories, and these are the parameters that are given to our constructor, namely the transportation costs, storage costs, stock storage costs, lead times, etc. MEN defines the graphs, like E stands for number of echelons, N stands for number of inventories, M stands for number of rows, etc. Once we have initialized it, there are a set of functions like get row and column, set state, etc. The important functions are the update functions, the reward compute functions, and the step functions. Let us dive into the code. In the code, we have defined the number of episodes as 100 because we have taken a small cycle, and the graph is small, so number of episodes, less number of episodes like 100 is sufficient. And when we come to this, we compute a random number here, and based on this random number, we determine what kind of action is supposed to be taking place. Like in deep Q learning, we compute the reward and select the action based on the most obviously good step, the most efficient step. But this might lead up to trapping up at the local maximum. In order to escape the trap of the local maximum, we are defining an epsilon here, that based on which we compute the probability when the action takes a random action. Based on this random action, we escape the local maximum. This epsilon is predefined by the code, and this is what gives us the optimal answer for the code. And when it comes to the action function, this is the function where the action is picked and values are selected from the array of the states for each action. For each action, we see which state has the best value, and then we select the action. And how are rewards computed? The rewards are computed using these functions and these variables, and based on the different values of the stocks and transportation costs, a total cost estimate formula is developed. And our objective is not to maximize the cost but minimize the cost. In this function, we are calculating reward in terms of cost, and reward needs to be maximized but the cost needs to be minimized. In order to solve this dispute, we need to develop a relation between reward and cost such that these both are inversely proportional to each other. For this, I have developed a theoretical maximum which the given graph is never going to reach, and subtracted the cost from the theoretical maximum, so that when the result, or otherwise the given reward, when maximized, the total cost of the inventory is minimized. This particular iteration, this particular adjustment yields us our answer. And now you may wonder, deep Q learning is a finite action space algorithm. Then how does something like inventory management, a continuous action space, actually work for this? For this is where the novelty of a project lies. This update function, based on the action of increase, decrease, or maybe no change. I have selected the current alpha to the possible maximum value. The alpha denotes the percentage of the change, uh, the percentage of change of the maximum given, the maximum storage of that inventory. Like for suppose a particular inventory has a maximum capacity of 5000 units, alpha denotes how much percentage of the inventory is supposed to be stored. Later on, we compute the number of objects by multiplying the total capacity of the inventory multiplied by alpha, and that's how we adjust the different quantities and select the action space. That's it from for my video. Hope you enjoyed it. Thank you.